As you're probably aware, I can't make it to class today because I'm in a meeting, but I would like you to watch this video and work through the activities that I've got on this worksheet here. First thing I want to do is start off by talking about why electricity actually flows through a circuit. And I think this first diagram that I've got here shows a pretty simplistic way of showing how electricity flows through a circuit, and you guys probably are fairly aware of the fact that it's the electrons that move through the circuit which causes the electricity to flow, and all of those products that we use every day that have use electricity. This is basically how it works, with the electrons flowing through the wires. Now, as I said, I think that's a pretty simplistic view of the way circuits and electricity works. I think the reason why I put this diagram here is because I think the most important part of this diagram is actually not the flow of electrons here, and is actually this bit here showing three minuses, or three negative signs there, three negative charges, and also the three positive charges at the other end. When you look at a power pack and you're using the direct current, you plug it into, you plug the wires into a positive terminal at one end and a negative terminal at the other end of the circuit. And that makes sense, to get the electricity to flow, positive, negative, and then that causes the flow, as in this diagram here. But I think the point that this diagram does show, but probably doesn't emphasize enough, is the fact that there should not be three negative charges here. There should literally be millions, billions, maybe even trillions of negative charges here. This is what sort of helps that flow actually happen, is because this charge here is enormous on an electric circuit to get the electricity to flow. Many, many more times than what it shows here, as I just said. The reason why that's important is because when I come down to this image down here on the next one, imagine that there is a massive negative charge here, okay? And now we're getting down to the atomic level. This is showing 4 atoms inside the metal wire, okay? Imagine that these 4 atoms are inside this wire. Now, if you set up a massive negative charge up this end here, you would know from the work that you have done on electrostatics before, is that that massive negative charge will actually push these electrons in this direction here towards atom number 2. What actually happens in that situation is that some of those electrons will jump over to that atom, okay, and move on to atom number 2. Then, other electrons might jump over as well. Now, as that process might flow through, and you have a couple of electrons or several electrons moving over. But I think one other thing for you to note here is that on this atom here, it has 5 positive charges. If one of those charges moves over here, that leaves an excess of positive charge. So you've got 5 positives and only 4 negatives, as shown in the red there. That actually has an additional effect to attract other electrons from this atom that way, and actually pulls more electrons over. And this is actually the process, remembering that this chain of atoms inside a wire would again be trillions of atoms long. This is what actually sustains the movement of those electrons through there, is because once this electron jumps over to here, it leaves an excess of positive charge, and that pulls more electrons in. So we've got the pushing of the negative charge over this side, the pulling from the positive charges when there is an excess of protons versus electrons when one of these jumps over here. And then the other thing that we need to remember as well, which is also adding to this effect, is on the far right hand side here, you have a massive positive charge, and that obviously has the effect of pulling even more electrons over. So this is why, even no matter how long almost a wire is, you will still have electricity flowing through, even if it's a really long way from this negative charge and the positive charge on either end. the electricity can still flow through because these electrons move from one atom to another, creating an excess of positive charge here, which sucks more negative charge across this way. And this is basically how electricity flows through a wire. And I think that that's one of the most important components of this topic. What I'd like you to do now is probably to go over that or replay the first part of this video here that I've been talking about and jot down some notes here about how electricity flows through a wire. I've started you off by saying electricity's moved through the wire, and that's what's shown in this diagram up here. But remember, I was saying that that's a very simplistic view of the way electricity operates in a circuit. The next thing that I'd like you to do once you've done those summary notes is I'd like you to have a look at, this is what we call the water analogy, or the water, sorry, that should be water flow analogy of electricity. And one of the things that we do in science quite often is we look at certain features of the scientific world and try and compare them to other things that we might find in the scientific world. And that's what we're doing in this situation here. What we're trying to do is we're trying to show that there is a similarity between the way electricity flows through a circuit and the way that water might flow through pipes. You can pretty much, I guess, to start off with, I'd rather you looked at this qualitatively rather than quantitatively, using some of these pressures and whatever this guy's name is, law or whatever, or Ohm's law here. I just want you to look at the pictures more than anything. And you'll notice here that here we've got a battery. As you would know, battery is what really supplies the power for an electric circuit. What we're doing in this analogy is we're comparing the pump, a pump here in water pipes, to the battery, because the pump is what supplies the energy to make the water flow around here. Okay. Likewise, the battery does the same thing in a circuit, providing the power to push the electrons or pull the electrons through the circuit. So one of the things that we might be able to do is have a think what we can learn from this analogy to try and make it simpler to understand. One of the main reasons we do that is because this you could actually see happening in the real world, whereas you can't see the electrons flowing through a circuit. So this is another reason why we use analogies in science. So I guess in this example, our pump represents our battery or our power source. This F, I'm assuming, stands for flow. And obviously the pump pushes the water through here. Likewise, the battery pushes the electrons through the circuit here and through the wires here. Then over this side here, we've got R, which represents a resistor. Now, a resistor is an area, and you know, even by looking at this analogy, this might help you to understand what a resistor is. A resistor is an area in a circuit where it's more difficult for the electricity to flow. And basically, it's a place where some of that electrical energy gets used up. A really good example here would be a light globe. So as the energy goes through the light globe, the electrical energy goes through the light globe. Some of that electrical energy is converted into light energy and also into heat energy, as you would be familiar with. And that uses up some of that electricity and some of that energy in the circuit. Here, on the water analogy, what they've shown is a constricted pipe, or a pipe that's much thinner than what the wire would be. And that's sort of another way that we might think about resistors, is that resistors they resist the flow. So this constricted area here, or where the diameter is much less than what it is in the normal pipe, or remember here we're comparing that to the wire, it basically shows what a resistor might do to a circuit. And obviously the effect that that is going to have on the circuit is that it's going to slow down or reduce the flow rate and take energy out of the circuit. And then once we get back over into this region here, we've got sort of the pump starting to kick in again and start pushing that around again. And likewise, that's what the battery does here, is sort of refresh that current and just keep it, maintain it. Now you might have a look at some of these statistical, or these extra information here, the numerical information here. Okay, and we'll definitely talk about those a little bit later on in the topic, especially Ohm's law here. What I'd like you to do now is in your books, and in your books, I want you to copy out this table here. And what I want you to do is, I want you to talk about these different things in the circuit, electrical circuit. I'll even put that in there, electrical circuit feature. And what is the water analogy equivalent here? So what is the water analogy equivalent to the flow of electrons in a circuit? And I would hope that you could. That one is pretty simple. Wires, likewise, I'm going to leave that one for you to do because it's pretty simple. With a light globe or a resistor, one of the ways that I like to think about it with the water analogy is to imagine that the light globe is a fountain connected here. So that fountain would shoot water up in the air and use up some of the energy of the flow there. So that's why I like that as a part of that analogy, is that the light globes and things that use up energy, I usually represent them as a fountain. But you might also be able to think of something else there. A water wheel is another one that often gets used in that water analogy, but I'll leave that one up to you. Then I want you to think about current flow through a circuit, and what would the water analogy equivalent be of current, electrical current flowing through this circuit here? So you might be able to write something down there about what you think that might be. Maybe possibly something to do with how much water is flowing through the circuit. Voltage is a little bit more difficult. It is an interesting little concept, voltage, and one that I'll talk to you about next lesson relates to a thing called, and scientists use these terms sort of interchangeably. We often call voltage potential difference, or another word for voltage is potential difference. So maybe you could have a think about the voltage on the power source. What would be the equivalent of that in the pump? So yeah, maybe for you to have a think about there as well. And then resistance. What represents resistance in the water analogy? How can you sort of express what's happening here with what's happening there? And I've pretty much already done that one for you, so that shouldn't be too difficult as well. Next question, or next electrical circuit feature I want you to have a think about is, why are the globes brighter if you double the voltage? So if you crank up the voltage here, why, and this was a light globe, why would this light globe get brighter? And remember, we're not just talking about the fact that the electrical flow here. What would happen to the resistor, or in this, if you doubled the pump pressure? What would happen there? And you might think about that in terms of fountain or a water wheel as well. Why, if you put in an extra globe, say you had one globe here and one globe here, why would those globes be dimmer? And what would you do here? What would you do here to show that, or to describe that? And look, you should be writing a couple of sentences here, and in fact, in many of these you could also be drawing, I think you should also draw a diagram here to show the flow of electrons, the wires. The voltage, as I said, it is a difficult one. If you can't get that one, that's okay. We'll go through that together later on, but see if you can have a go. And then drawing some examples here. Now, the next one I've got there is a series circuit. Now what I've done here is shown you a series circuit. Okay, this is the light globes. This is a circuit diagram of this. So these are basically the same diagram here. And I found this diagram on the web as well, showing if you've got two areas of resistance there. So I've sort of done that one for you and shown you that in a series circuit, if you add an extra resistor, okay, this is what happens in that situation. And you could also compare that a little bit to this one here. Why are the globes dimmer if you add an extra globe? Then I want you to try and come up with something for a parallel circuit. You might start with a circuit diagram and then draw what happens there. And obviously in a parallel circuit, you need to create a second path for the other light globe or the other resistor there. These ones, there's only one path for the electricity to go through. So for the parallel circuit, you'll need to show a second path. It could be around the outside or could be anywhere, but it could even be up here above the pump. But you need to show a second and draw this in your books, a second resistor there. A couple of other things here I want you to talk about which have to do with safety. These three here and the two down the bottom. Faulty wiring. How would you represent faulty wiring in this sort of arrangement here? How would you represent electrocution? So you think about what happens in an electrical circuit when someone gets electrocuted. What happens to the electricity in this circuit? How could we show that in the pump there? And also insulation, about why insulation might be important there. There you might think about if the water was hot going through this pump system here. If the water was like really hot, 90 degrees Celsius or something like that, how would you represent insulation in that situation? And then a fuse or circuit breaker and an earth wire might be two other things for you to think about as well, and I'd like you to show those, how they work. How would a fuse work in this circuit here, or a circuit breaker? What would they do? And then an earth wire, what would an earth wire do as well? That one might be a little bit difficult. That's another one that sort of goes in with the voltage one. So if you can't get that one, that's okay. Just have a little think about it for a couple of minutes, and then if it's too complicated, just move on. And then last two, these two here, why does an ammeter, which measures, just put that in there, which measures current, why does that need to be placed in series in the circuit? So why does it need to just be one pathway for that? And why does a voltmeter, which measures volts, need to be placed in parallel? That's another really difficult one because it's obviously related to voltage and potential difference. So again, have a think about that one, but if you can't get that one, that's okay. Here, what I'd like you to do next after that is move on to completing this table and listing the advantages and disadvantages of series and parallel circuits. If you need to use the water analogy to do that, great, that's fine. But I imagine you'll be able to research this fairly easily too, and that might not take you that long. But really important to think about the advantages and disadvantages, especially when you do the next thing, because what I'd like you to do, I'd like you to draw a circuit diagram of the lights in the room that you are in at the moment. Have a look around the room, have a think about where the lights go, where the wires go, sorry, I should say, and where the lights are positioned, where the light switch is, and remembering that, or one of the things that you should be able to do is say whether the lights in this room are connected in series or parallel, how you know that, and then that should inform your process of drawing that diagram as well. Now, I think if people do that properly and they do it in their books, that work should take you pretty much the whole lesson to complete. But I know that sometimes people feel that they need to share their work with other people, which they can't do anyway because they're doing this in their books, okay? But, I want this done properly, and I want to be able to walk back in and discuss this with you guys next lesson as well. So if you can't do that properly and you finished all that work, then good luck for you. You've got some extra work to do out of the textbook, which is read pages 92 to 102 and answer those questions there. And so that's all for you guys to go through. I will share this with you, but again, I can't highlight enough the fact that I want you to do this in your books, not on your computers. I'll share this document with you so that might make that process a little bit easier for you anyway. Okay? All right, so have a good lesson, and I'll see you guys next time. And obviously, I still need to go through your exam results and just check a few answers as well. And I might have some good news for people, hopefully, on that coming up next lesson as well. All right, I'll